story about, man, that was kind of cool. But only a parent would think, oh, that's kind of cool. So yesterday was my husband's birthday, and our granddaughter got to pick out a balloon, and she got to pick out an ice cream cake for him. She picked out a camouflage ice cream cake. That's kind of funny. But at Hy-Vee, when she was picking out the balloon, she came home with a balloon that says Happy 65th birthday. Well, my husband's not 65. You know, that was a compromise. Her first choice was breast cancer awareness. So the 65 was much better. So last night, right before supper, my son-in-law got the cake out of the freezer so it could start to melt. It wouldn't be so hard to cut. Well, Claire, that's all she wanted was a cake. She didn't want to eat her supper, she wanted the cake. And she wailed and wailed and wailed, and you know, I mean, not cry, but kind of just obnoxious wailing. So finally we said, all right, let's just give her a piece of cake. So we got her a piece of cake. She just had it. She didn't even eat it. She fed it to me. She ate a little bit, and then she went and ate her supper. I thought, really? She was not going to eat her supper. No, she wanted cake. She didn't want her supper. She wanted cake. She didn't want her supper. But once she got her cake, she was fine eating supper. So I thought, in all of these years, you tell kids, no, you can't until you eat your supper. I never thought about, why not just give in? She got bored. It's not going to work for you guys. Don't try it. Yeah. Don't try it. Okay. Oh, and we got PCR products. Yes. Biochemistry after all of that. PCR products. Okay, so I'm going to finish up P53 a little bit, and then we'll go on to talk about apoptosis. I put a couple more papers out. And I noticed that some of you penciled your name on. I'm leaving those papers in the folder just in case, you know, you decide to change your mind. So we might be going back and, so I'll just leave all the papers in unless, you know, just in case you want to change your mind. And you can reshop, you can return and exchange. So. All right, so I just wanted to look at the primary sequence of P53 and a little bit about there's the C-terminal N. The N-terminus is a busy, it's kind of a busy part of P53. Okay, it's the site with all of the phosphates. Okay, so this means that if you're going to phosphorylate P53, it's there in the N-terminus. So that's where ATM would phosphorylate P53. That's where checkpoint kinase 2 would phosphorylate AKT. It's also the MDM binding site. And they couldn't find out whether or not MDM2 could or couldn't bind to phosphorylated P53. Okay, this is also the activation. Okay, and what that means is that this is the part of the protein that leads to the gene activation. Okay, that's the part of the protein that you need in order for P53 to activate the transcription of its target genes. And that's because, as some of you in genetics knows, it is the binding site for CDP P300, which is an enzyme that adds acetyl groups to the promoter region for the target genes. Okay, then there's a big DNA binding domain. Okay, and then tetramerization domain. Okay, so when P53 forms its tetramers, it forms its tetramers by binding to, binding in those regions of all four P53s. Okay, most mutations, if you inherit a mutant RAS, or if you develop a mutation, in the P53 gene that leads to cancer, most mutations are here. So P53, even if it's turned on by ATM and checkpoint kinase, if it can't bind to the DNA, it can't activate its target gene. I wonder if there's some, I bet there could be some pretty wicked mutations in the tetramerization domain too. Okay, and then human papillomavirus. Makes an enzyme called a protein. A protein called E6. Okay, so I think the proteins in human papillomaviruses are named by when it is in the course of a replication or virus production they're actually synthesized. So I think E means early. So this is one of the proteins made early in the viral infection, and it binds to the DNA binding domain, to this region. So this is how the human papillomavirus keeps the cell alive so it can replicate. And it's also another protein, so it's one of the proteins also that human papillomavirus produces that causes cancer, that leads to cervical cancer. So there's some strategies out there looking for, is there any way we can knock out E6 activity? Okay, there's another protein, E7, of papillomavirus, HPV, okay, that inactivates retinoblastoma protein. Okay, so E2F transcription factor is always active. So it's pretty well known how human papillomavirus is actually oncogenic. Finding target drugs has been a little bit more challenging. So if anybody finds a paper in that area, there's actually quite a few, but they kind of end up going in different directions because of some of the different binding domains that E6 has. Okay, is that okay? So that's the primary structure of P53. All right, now I want to go through and look at, kind of think about how can you block P53 activity so that even if the cell has normal P53 genes, it still doesn't have P53 activity. Okay, so there are other ways besides mutation. Knocking out okay, so I'm going to give you, this has too many clues in it. I'm going to give you a pathway. It's actually a pathway I found in a Nature Reviews article. So I'm going to just show you what the article, what the figure looks like. and then we'll see how much meaning can we pull out of the figure. Okay, so this is a retinoblastoma protein. There's an arrow, that's a block, okay? Blocks E2F. Okay. And that leads to, just like every other protein is a square. This is exactly how it is. ARF, okay, which leads to block. MDM2, which leads to a block. Okay, so that's the only deviation I made from the article. Okay, I kind of like this figure for a lot of different reasons. So how is it that retinoblastoma blocks E2F? Yeah, it's just. And what's E2F? And I think E53 is bound to it. So one of the genes, and since we're looking just at this, one of the genes that is not getting transcribed is ARF. Okay? Oh, I'm sorry, that's what should I, this is wrong. I should be retinoblastoma protein. And what does ARF do? If ARF were made, what does ARF do? Binds to P53. I'm going to put some MDM2 papers out. I think there's at least one MDM paper in the envelope, maybe two. MDM2 polyubiquinates P53 for destruction. Okay, so given this pathway, does that make sense? You recall everything that we've at least covered everything? There hopefully shouldn't be anything strange. Okay, so what kinds of alterations in this pathway could lead to the loss of P53 activity?
An increase in the amount of ARF, or sorry, a decrease in the amount of ARF.
Yeah, yes, that's one way. As a matter of fact, let's see, mutations in the gene that codes for ARF you can find in cancer cells. Okay, so if you mutate ARF, I'll just say mutant ARF, leads to loss of p53 activity because it can no longer protect p53 from MDM2, and sometimes gene silencing. In other words, the gene that codes for ARF is silenced by DNA methylation, and then that gene can't be turned on anymore, so we lose ARF. Nothing will happen to ARF. It's not mutant, but the DNA, but the gene is permanently turned off. That would be a bad thing for p53 because it can't rescue ARF. If you lose ARF, then p53 can't be rescued from MDM2. Okay, so yeah, that's a good one. And that one, and we see that in cancers. Okay, anything else?
If MDM2 is permanently activated?
Yeah, you can get overexpression of MDM2. So MDM2 is overexpression. That's a common feature of cancers, is there's just too much MDM2 activity. And there is an MDM2 specific drug that's given to cancer patients, and that's why it's so kind of easy to find papers about knocking out MDM2 activity. So if you are looking, kind of want to shop around for your own paper, a drug called Nutlin 3 inhibits MDM2. I think, Carly, did you pick a paper that's looking at MDM2 and NF-kappa B inhibition? I can't remember. I think it
No.
was dual.
It was like MDM2 and then the phosphorylation of AKT.
Oh, that's right. Okay, the role of MDM2 in the AKT pathway.
Mm-hmm.
Yeah. But I think I put one out there in the box that looks at what happens when you inhibit MDM2 activity and NF-kappa B activity. Okay, any other way?
An overexpression of the retinoblastoma protein.
Let's see. Overexpress.
Because then there's no E2F making ARF.
That looks like it would do the job, but it turns out that it's not, because in so many other ways, retinoblastoma protein is a tumor suppressor gene. But you're right. I mean, your line of reasoning, just given this pathway, sounds reasonable. Look at P21. What else? What could happen to P21? That would make it look like P53 was not active. Yeah, if you mutate P21, or you silence the gene, that would be a bad thing. So, and as a matter of fact, you can find lots of cancers with mutant P21, or the gene has been silenced through DNA methylation. So there's lots, and we didn't even talk about, what would happen if ATM, what would happen if ATM was mutant, as it is in people with ataxia-telangiectasia? How does that affect p53 ability?
Well, it can be phosphorylated, first of all.
Hmm?
First of all, it can't be phosphorylated.
Yeah, and if it can't be phosphorylated, it can't be active. So people with who have ataxia-telangiectasia have a hard time activating their p53 gene. So when you get irradiation therapy, okay, some of the cells are just outright killed. I mean, the DNA is just chewed up by all the double-stranded breaks. Okay, but a lot of the cells are not damaged to death, the DNA is just not fragmented to death, but the idea is if you damage the DNA enough, that should activate P53 for the cell to commit apoptosis. How would that work, and how effective would radiation be in cells in cancers with mutant P53 activity? Not terribly, yeah. You just have to hope that you're getting the tumor by just outright blasting away and killing and going by the kill route rather than the apoptotic route. Okay. Anyway, so this is, there's tons and tons of pathways. If you like, Sean Desai last year loved looking at pathways, and he would have pathways up to wazoo from the internet. You can do that if you want. About P53 and MDM2, and all of the checkpoint kinases. Oh, but here we go. But what I want to do is switch over to apoptosis. So, all right, we're going to look at, there are, we used to think that that all cells died by necrosis, and I'm going to tell you what necrosis is. Then somebody discovered apoptosis. Oh, so now we had two ways for cells to die. And then somebody discovered death by autophagy, so then there were 3 ways. And now there's actually several ways a cell can die. Okay? But most cells die either by necrosis or apoptosis. So I want to look at what's the difference between the two. And why don't you want to go by necrosis? Okay, and apoptosis. So we're going to start out with the normal cell. I'm just going to make it round. And it has a nucleus, and it has a whole bunch of organelles. It has a nucleus and a whole bunch of organelles. Okay, but if a cell is going to die by necrosis, it's sort of dying because of the lack of the ability to make ATP. So ATP is not being made, and so what happens to osmosis, do you suppose, if a cell loses its ability to make ATP? About the sodium-potassium pump on the cell surface. If the sodium-potassium pump's not working up to speed, what's going to happen to osmosis? Yeah, water's going to be taken in. And so the cell begins to stretch and it gets bigger. Okay? And then pretty soon, so that's one of the every organelle seems to fatten up. Okay, so water's being taken in like crazy, and these AR is beginning to fatten up, and the Golgi is beginning to fatten up. So everything is swelling because osmosis is drawing water into those, into the cell, into the organelle. So we see a swelling. Okay, and pretty soon, the membrane explodes under the arrow, and stuff spews out. Okay, just garbage is spewing out of the cell. Okay, there's still some junk in here. Okay, but the cell kind of explodes. And all of the junk that used to be in the cell is not now outside of the cell. And this leads to inflammation because this is like a picnic for immune cells. Okay, so this is actually an extremely dirty death. Okay, so inflammation is triggered by the exploded garbage. Okay, so it's really a messy death. And it has some pretty bad consequences to you, because you don't want to, you do not want to incite inflammation. Okay, so some cells die that way, by necrosis. It's really caused by the loss of ATP. It is reversible. I mean, if you can restore ATP, the ability to make ATP, you can go back to normal. Okay, so apoptosis, on the other hand, the cell is going to be continually shrinking, and actually apoptosis is ATP requiring. You cannot commit apoptosis if you don't have enough ATP. So it's an ATP-driven process. The cells shrink. So actually, and the chromosomes condense, or the nuclei, well, chromosomes condense, so the, okay, so I'm supposed to be drawing a shrinking cell. Okay, so I'll tell you that the cell shrinks, the chromosomes condense, the DNA fragments at the same time. Okay, and these little blebs form. Okay, and the blebs contain little organelles, it might contain mitochondria or ER, but there's stuff inside these little blebs. And these little blebs break off the cell that's committing apoptosis as these are called apoptotic bodies. They're membrane enclosed cell garbage. Okay, so in necrosis, that stuff just explodes out of the cell. Okay, in apoptosis, that garbage is packaged into little apoptotic bodies, so it never really is a pretty clean process. And eventually, here's a garbage-filled sack. Eventually, a macrophage will recognize that. And will phagocytize the apoptotic body and digest the components of the apoptotic body. So it's an extremely clean. It does not involve inflammation because you're not exploding garbage, cellular garbage all over the place. You're packaging it up and letting the macrophage take it in and digest it. Okay, so this process of moving into this kind of this cellular feature where you're breaking down the DNA, the chromosomes are condensing, you're forming these blebs, that's the part that's ATP driven. Okay, so there are a couple things I wanted to talk about in this process, and then we'll talk about kind of some overview. But I have to tell you that, and I tell the story every year because it was so true. So back in 2008, it was a semester where I was teaching an overload. I was teaching just like now, I was teaching molecular genetics and cell biology. And both courses, I had them write papers. And so, I mean, I was just reading papers like nonstop. And right at the end of the semester, Rich's aunt, who lived in Chicago, died. And, oh my gosh. And there's no family. And we got to know a little bit about Aunt Annie, although we sort of knew this before, by what the people were talking about at the funeral. Apparently she was not well liked. You don't know about anyway. So all these things come up. But anyway, so we went that night. I can't remember. We did stay in a hotel, but we met Rich's two of Rich's siblings also drove to Chicago. Rich's brother rode with us, and so I sat in the backseat grading papers all the way to Chicago and all the way back. But we get to the house, and that woman committed apoptosis. It was just incredible. I mean, everything was in a box. It's like she packed up her house and went to bed and died. It was absolutely amazing. It was the best metaphor I'd ever seen for apoptosis. I should have taken pictures. And we went down into the basement of her house. Everything was boxed. All of the bills and leftover paperwork was in the top drawer of her dresser, so Rich just pulled the drawer out and took it home because he ended up being the executor of all of her estate. It was just, she was pretty incredible. I can tell you my mom is not going to commit apoptosis. It's going to take forever to clean up after her. So, but I thought, whoa. So I brought home, my sister-in-law looked at the really nice leather gloves, and she said, and her hands were, I have kind of small hands, and Auntie had small hands. So Judy, Rich's sister, said, do you want these gloves? And I said, yeah, because they were really nice. So my daughter said, you're wearing the gloves of a dead person? Someone's got it. So she was this. She had boxes, and we now have some of her boxes of things in our barn. One of which is a set of nice 1950s style dishes. So we can be really retro. And she lived in the Polish neighborhood of Chicago, and we went to, so the mass was at a Catholic church in her neighborhood, and there was not a single thing in English in that Catholic church. It was incredible. I mean, so we were sort of, didn't know what was going on. So anyway, so that's apoptosis. Okay, so what we're going to do, let me check my, oh, there is a couple things I want to do before we go on to the overview. Okay, so necrosis is a cell explosion.